Hello everyone, my name is Raja Harshit Modi and today I'll be going to shed some light on a topic of theory of computation, that is closure properties of CFL. CFL is context-free languages. So context-free languages are closed under union, concatenation, star closure or clean closure. Union, you can say that if L1 and L2 are context-free language, then L1 union L2 will also be context-free language. With concatenation, if L1 and L2 are again context free, so L1 dot L2 will be also a context free language. And for star closure, if L1 is in CFL, then L1 star will also be a CFL. So this was a basic outlook. In further video, we will prove these languages and with some examples. So let's start. So we should considering L1 and L2 are context-free languages. L1 is generated by grammar 1 and L2 is generated by grammar 2. Grammar 1, grammar 2, G1, G2 are represented by V, T, S and P. V will represent the number of set of terminals, sigma will represent set of terminals, S will represent start symbol of grammar G1 and P1 will represent production rules for grammar 1. Similarly for G2, V2 will represent set of non-terminals, sigma 2 will represent set of terminals, while S2 will represent start symbol for grammar 2 and P2 will represent production rule for grammar 2. Also in this video we will discuss CFL are not closed under intersection. Complement intersection is L1 intersection L2 and complement, as you can see here. These two also we'll discuss. So let's start with proof of union. So our query statement is if L1 and L2 are context-free languages, then L1 union L2 will also be context-free languages. Let's start a proof. L1 grammar 1 V sigma PS we have discussed it, above. These notations will be same regarding all the video for avoiding confusion. L2 grammar 2 non set of terminals, set of terminals, start symbol and product rule and start symbol. CFG context free grammar production rules. As we know that context free grammar rule is A implies to alpha, alpha belongs to variable A, V, and alpha belongs to V union T star. So finding union G1 union G2 G3 V1 V2 sigma product and choosing between S1 and S2. So in union all the values are satisfied, hence we will say it's proved. Now talking about concatenation, again L1 and L2 are two CFL, then L1 and L2 will also be CFL. Notations are the same as I have said above. L1 L2 G1 G2 G3. Product rule, the new grammar 3 will be V sigma PS, P will be the production rule and choosing between S1 S2. So let's stop with an example. Considering G1 S, considering an example grammar G1, S derives AA and A derives A. So is it a CFL? Yes, it is a CFL. So CFG in this will generate power of A. G2 drive in grammar G2, S2 will drive B and B will drive B. This is also a CFL that will generate power of B. So for concatenation, S1 S2 L1 L2, and putting the values in S1 A square, S2 value A square B square. Concatenation is proved here. Okay. For star closure, for clean closure, if L1 is content free language, obviously it has to be. It's clean closure, L1 star, see, will also be a context free language. For taking an example, L1 language 1 A to the power n B to the power n, where n should be greater than equals to 0, is a context free language. Then L1 star A to the power n B to the power n will also be context free language. So from these three we can derive that CFL are closed under clean closure, under union, and under concatenation. Now let's talk about intersection and complementation. For this also we have to consider L1 and L2 should be context free languages, and this is directly the result, but we'll explain in this part. Let L3 is in another language. If we do intersection, it will not be a context free language. So let's talk about it. Taking L1 language 1 A to the power n B to the power n C to the power m, where n is greater than equals to 0 and m is greater than equals to 0. L2 A to the power n B to the power n C to the power n is greater than equals to 0 and m is greater than equals to 0. So L3 L1 intersection L2, the output will be an bn cn, as you can find from here, need not to be context free, because L1 says equal number of A should be equal number of B's, and L2 says equal number of B should be equal to equal number of C's. Their intersection L2 says both conditions to be true, but push down automata can only compare to, hence not true. Similarly, complementation of CFL N1, which is set of terminals star minus L1, need not to be context free. So this was the theory part. Let's take an example. Consider the languages L1, L2, L3. L1 is A to the power m, B to the power m comma n greater than 0. Similarly with L2, A to the power n, B to the power n. L3, A to the power n, B to the power n, C to the power n. So a query is to find which one is not true. PDA, so these are four of the options. Let's talk about them. PDA can be used to recognize L1 and L2. So PDA can used to be recognize L1 and L2. L1 contains all the strings followed by number of A's and followed by number of B's. So it can be accepted by PDA. L2 contains string with n number of A's followed by n number of B's. It can also be accepted by PDA. So we can say option A is correct. Talking about option B. Option B says L1 is regular. It is true. As regular expression, L1 is A star B star. Okay. B is also true. For option C says L1, L2, L3 are context free. L3 contains all string with n number of A's followed by n number of B's followed by n number of C's. But it can't be accepted by PDA. We have discussed in the starting part of the video. So C is the wrong option. Talking about D. Turning machine can use to be recognize all the three languages. Yes, this is correct. So D. Jumping to example 2. The language L 0 to power I 2 to power I greater than 0 over the alphabet 0, 1, 2, 3. We have to find which is not recursive, is recursive, and deterministic CFL. So the above language is deterministic CFL as for zeros. we can push O on stack and for 2's, and we can pop corresponding O's. As there is no ambiguity which moves to take it is deterministic. So option B is correct, as CFL is a subset of recursive. It is recursive as well. So thank you.